Hi everybody. In this bonus video we're going to talk about what happens to something, an axial member, when we spin it and how much it elongates due to that. So for this specific bonus video I've chosen to take a look at what happens to an airplane blade as we spin it, but in reality you can think of anything that spins, it's going to elongate. Off the top of my head I can think of like a dentist drill. Probably not going to elongate much, but if they're digging around on your tooth, that little bit of elongation due to the spinning might be worth consideration. You can think of a windmill that produces electricity. Alright, those blades are going to elongate somewhat too. Maybe not significantly, but, still somewhat. Anything that spins, it's going to get longer. We could think of that intuitively. Alright, so maybe when you were a kid, you grabbed your one sock, you balled up your other sock and shoved it inside and spun it around and hit your brothers. Alright, at least I did that. And after a while, the sock gets really long. Okay? Now, if you didn't beat around on your brothers with a sock in another sock, imagine an elastic tied to a rock, and you spin that elastic around, the elastic's going to get longer. Alright, so in this case, it's exactly the same, it's just the elastic is a little bit stiffer. So let's look at this specific question I dreamed up for the purpose of this video. So I said, given this specific situation here, with the outer diameter of the blades at rest being 1990 millimeters, and the inside of the casing being 2000 millimeters, what is the max RPM the blades can be spun at before they hit the casing? Alright, so this, I'm not quite sure for sure, but I'm pretty sure this is an analysis that an engineer at Boeing would do, because as you'll see in the answer we get, it's considerable. So, airplane turbines, I did a little bit of research. They're made out of nickel-based super alloys, alright? So very specialty materials. And I just found the E for nickel was to be that. And for the area, alright, I just guessed it to be about 15 centimeters. But in reality, the area, looking at a cross section, like this, it's going to look something like this. Kind of tear-shaped down like that. Alright, now you'd have to do some other fancy analysis to find this, maybe some sort of integral. And plus the area is not just like changing like with a cross section, it's also changing with the distance from the radius. But for this question, let's assume it's a constant 15 centimeters. Alright, so that seems reasonable to me. And the density of the specific nickel was that. So let's get into this. How in the world are we going to find the elongation? Well, we know from the parameters of this question, our elongation can't exceed this distance here. That distance there is just going to be the outer diameter minus the inner diameter, right, divided by 2. Okay, so we can do that here. Our delta, 2000 minus 1990 by 2. The max delta we can have in this case, 5.0 millimeters or 0.005 meters. Okay, so in order to find the elongation of something, we need to satisfy this equation here, right? We've been going through this one for a while. N dx over EA, and potentially any one of these could be changing with x, but since I fixed E and I fixed A in this problem over here, we don't need to worry about that, so we just need to find the normal force as a function of x. Alright, now this is kind of tricky because there's no applied force. Alright, it's kind of like temperature. You're not applying a force, but as a result of what you're doing, you're getting a force. So let's just take a look at one of these turbine blades. Alright, I'll draw it here. Like this. And we'll start our x coordinate from here. Okay, and we're going to take a specific cut right here at a distance x away. And of course it's going to be of a length dx. Okay, so let's blow that piece up a bit. Over here. Cut edge. Cut edge. Alright, so what's going to be going on here? Well, since it's a length dx, let me quickly just remind myself of that. There's going to be some normal force on this side here, N. And on this side it's going to get a little bit bigger, N plus dN. Alright, and I just put the bigger normal force on this side because as you go further away from the center of something that's spinning, the normal force gets bigger. Okay? So that's basically what it is. It's a certain N here, and it's the same N here plus a little bit different portion of N. Okay? And like usual, we'll label the directions here quick. And the sum of the forces in the x equals 0? No, okay? In this case it doesn't equal 0 because we have an acceleration. Okay, so it's going to be equals mass times acceleration. Alright, now we're going to use a different form of acceleration and then just, straight old acceleration, but we'll get to that. So, doing this here, we get n plus dn, that piece, minus n, equals mass times acceleration. Now you can imagine this little infinitesimally small piece has infinitesimally small mass, alright? So we'll call that dm. And then an acceleration a. We'll call it centripetal acceleration. Give that little C right there because that's what it is, right? Alright, so let's keep going here. We know that from one of our physics courses, centripetal acceleration is equal to omega squared r. So distance away from the center. In our case, I'll call it x. Okay, where omega is like radians per second. So we can rewrite this. N goes away. We can say that dn is equal to dm. Alright, what is dm? Well, that's rho a dx. Alright, because our density is units of kilograms per meter cubed times the area, meters squared, times the little bit of length, meters. So it turns out all these units cancel off and we're left off with just mass. So this is dm. Okay, and then a, just plunk this down here, w squared x. Just like so. So to find the total n, we just integrate this. So n, function of x, is equal to the integral of this. Rho a omega squared x dx. Now all of this is constants, comes out, and you can find out the final normal force as a function of x is going to be rho a omega squared x squared by 2. Alright, we just simply integrated that x with all these other constants. Okay, so moving along, now that we have normal force as a function of x, we can go back and plug it into this equation here and integrate to find the total elongation. We're not finding the total elongation, we know what the total elongation is. We want to solve for omega. In any case, it's kind of the same process. So, delta equals the integral from x equals 0 out up until the very end of the wing. Alright, up to L. And then we put in all our constants here. The normal force as a function of x is this. Rho a omega squared x squared by 2. And then of course we have EA in here too, right? Still. Because we still have to consider EA here. And x squared dx. That's it right there. And we integrate this, evaluate it. Alright, we can find it's just going to be rho, notice the a's don't actually matter, w squared x cubed by 6e. And then of course we can evaluate it at 0 to L. When it's 0, this whole thing is nothing. When it's L, we're just going to get this. Alright, so in this question we want to find out what omega is, alright, because that's radians per second. We want RPM, but that's just a conversion. So let's just rearrange this. Omega is equal to 6 epsilon e over rho L cubed square root. And plugging in all the numbers, if I did this right, we get 779 radians per second. All right. Now asking for RPMs because engines are usually, rounds per minute. So we know that 779 radians per second times, well, it's going to be 1 revolution per 2 pi radians. Okay. Now we're at revolutions per second. But we want rounds or revolutions, same things, per minute. So we're going to say times 60 seconds per 1 minute. And the seconds go away, and the only units left is revolutions per minute. Ta-da! That's exactly what we want. Turns out we get 7442 RPM. There we go. That's the final answer. And let's just do a common sense check, because any of these questions we kind of dream up. We need to use our common sense. Does it make sense? All right, approximately 7,500 rounds per minute. Yeah, that's pretty fast, but that seems about reasonable for an airplane engine going at full speed. All right, so if you want to make this question more interesting for yourself, all right, you can take into effect the temperature. You can imagine a plane taking off in a place like Dubai, and then it's going up to like -40 degrees. All right, what happens like that? And just to throw a thought out there, what do you guys think about the elongation due to the weight of this spinning propeller? All right, because when it's up here, if it's stationary, it's going to get shorter. If it's down here, if it's stationary, it's going to get longer. So I'm kind of wondering, does it go through like this cycle of like maybe some sort of sine wave, if you're getting longer or shorter at the top, longer at the bottom, maybe kind of forming this sort of shape, or how much does time affect this spinning propeller? All right, let me know about your thoughts. Hit them in the comments below. And hope you enjoyed this video. We'll see you around.